Good morning, sir. I am G. Baba Sohail. I am from CSCA section. My topic is about classical free electron theory. Into the topic, classical free electron theory. Introduction to classical free electron theory. Classical free electron theory explains the behavior of electrons in metals. It is a model that treats conduction electrons as a gas of free particles. This theory helps in understanding electrical and thermal conductivity in metals. Moving to next slide. Historical background. The theory was developed in early 20th century by physicists like Drude and Lorentz. It arose from the need to explain the conduction properties of metals. The model is rooted in classical mechanics rather than quantum mechanics. Basic assumptions. Electrons in a metal are considered as a free particles that can move without a restriction. The interaction between electrons and ions in the lattice is minimal for conductivity. The temperature dependence of resistivity is a key consideration is model. Electron gas model. Electrons are treated as gas of non-interacting particles. The density of conduction electron influences the conductivity of material. This model simplifies the complex interactions within a solid. Drude model. The Drude model is a key component of classical free electron theory. It describes the motion of electrons in response to electrical field and thermal energy. The model predicts that current density is proportional to the electrical field applied. Electrical conductivity. Electrical conductivity is a measure of a material's ability to conduct electrical current. In the context, the classical free electron theory, it is related to the density and mobility of electrons. The formula for conductivity includes parameters like electron charge density and mobility. Ohm's law. Ohm's law is derived from the classical free electron theory framework. It states that the current through a conductor is directly proportional to the voltage across it. The theory provides a physical explanation for the linear relation described by Ohm's law. Temperature dependence. The theory posits that electrical resistivity increases with the temperature. This increases due to more frequent collisions between electrons and lattice ions. The classical model provides a linear relation for resistivity with a temperature changes. Limitations of the theory. The classical free electron theory fails to accurately predict specific heat capacities. It does not account for the quantum nature of electrons at low temperatures. The theory also struggles to explain phenomena like superconductivity and magnetoresistance. Comparison with quantum theory. Quantum theory provides a more accurate description of electron behavior in solids. Unlike classical theory, quantum mechanics accounts for wave particle duality. The difference becomes significant at small scales, high frequencies. Applications of classical free electron theory. The theory is fundamental in understanding the properties of metals and alloys. It aids in the design of electrical and thermal conductors in engineering. Concept of theory are used in semiconductor technology as well. Relationship with band theory. Band theory extends classical free electron theory into quantum realm. It explains the formation of conduction and valence bands in solids. Understanding electron mobility requires both classical and band theory perspectives. Mathematical formulation. The mathematical formulation includes the drift and velocity and acceleration of electrons. The equation for current density includes charge, number density, and drift velocity. These equations allow for calculation of conductivity and resistivity. Electron scattering. Scattering events are central to understanding resistivity in metals. Collisions with lattice ions and other electrons impede free movement. The mean free path of electrons help quantify how far they travel between collisions. Role of lattice structure. The arrangement of atoms in a lattice influences electron behavior. The different lattice structures can lead to variations in conductivity. Understanding the lattice is crucial for materials, science, and engineering applications. Thermal conductivity. Classical free electron theory also applies to thermal conductivity in metals. The movement of electrons contributes to the heat transfer within the material. The theory relates the thermal conductivity to electrical conductivity through the Weidmann-Franz law. Modern relevance. Despite its limitations, classical free electron theory remains relevant in materials science. It serves a foundation for more advanced theories and models. Understanding the classical theory is essential for grasping the evolution of solid state physics. Conclusion. Classical free electron theory provides a fundamental understanding of electron behavior in metals. While it has limitations, it serves a critical stepping stone in solid state physics. Its interplay between classical and quantum theories continues to shape modern research. Thank you.